This paper that didn't appear in the proceedings because once I submitted, I got the reviews, but I also improved the results, and I presented these improved results in two places. A preliminary result was presented in this journal here, and it was further improved in a workshop at an international conference on machine learning, and I will summarize somehow the results here very quickly. Okay, so there's no paper in the proceedings. Okay, so what is the overview and the main contribution? I will mostly rely on a very nice paper that appeared by Kobayashi this year, who shows that there's one way to express the Fisher-Rao geodesic between multivariate normal distribution with boundary condition. Okay, I will explain what that means, and based on that, I will design a very simple and efficient guarantee 1 plus epsilon approximation of the Fisher-Rao distance for Gaussians. And because this will be a bit time consuming, even if it is very now numerically stable, I will also present a different metric distance for Gaussians based on some special embedding into a higher dimension of the SPD cone. Okay, so just to recall what is the Rao distance and Fisher-Rao Riemann geometry, you take a regular statistical model, P lambda, where lambda lives in a convex, open convex domain upper lambda, and you take the Fisher information matrix, which is the covariance of the score, and you will derive, because it is for regular model, it is positive definite. You can interpret it as the coordinatization of the Fisher metric tensor. And Rao and also Otening define the Rao distance in a very old paper in 1945 and also in 1940 as the geodesic distance for the Fisher metric. Okay, and basically we want to compute the geodesic distance between two multivariate normals. So basically I need to do two things. One is to compute the Fisher information metric. One is to know the expression of the geodesics with boundary condition, and then to integrate on the geodesic the length element. So this is in 1D. 1D was a very well-known event for the 1930s, almost a century ago. In that case, you can show that the Fisher information metric for the usual parameterization mu and sigma is a bit deformed Poincaré metric, and from the Poincaré distance in upper plane or hyperbolic disk, you can derive a Rao distance very easily. And in that case, we have constant Gaussian negative curvature. Okay, and this is very well known, so that you can measure the distance between two univariate Gaussians and design some hypothesis statistic test based on geodesic distance. Actually, you can also rewrite the Rao geodesic distance as this expression, where this term here is called a Möbius distance. Okay, and I just want to show you a few geodesics. This is a metric tensor here that you will see as Tissot indicatrix. I will skip that part for now. And our goal is to make the generalization for multivariate Gaussian here. Okay, so this is a Fisher information metric, and it has been studied by Len Skofgard in 1984, a famous paper, the Riemannian geometry. We got the length element for the multivariate Gaussian, which is expressed as follows. And an important thing is that when dimension is greater than 1, we don't have constant sectional curvature, and even we have some positive sectional curvature. So it's not NPC, a non-positive curve space. So yeah, we always say hyperbolic geometry, which holds for like a product of disk or diagonal Gaussian, but the general multivariate Gaussian is a bit special because you can have positive sectional curvature. So what was even in the 80s known is that there's some invariance of the length element by the positive affine group. So this is a positive affine group with the group operation here and the inverse. And this group, you can embed it as a matrix group by taking this embedding to matrices. And what you will have is invariance by the action of the positive affine group on the Rao distance. Okay? So basically, because you have this invariance, you may always assume that one of the two arguments of your Rao distance for multivariate is a standard normal. This is very well fact. And also in the 1984 paper, you have already the second order ordinary differential equation of the geodesics that you can derive from the first order differential equation of the parallel transport. This is just a usual thing. So you have this general expression if you have a regular model with parameter theta. Here we have a model with one part which is vector and another part which is positive definite matrix. So this is why you have these two equations that are linked here. But basically, if you take a pair of vector matrix, you can have a single things here. And we may consider to solve this ordinary differential equation either by setting, as I said, we can always assume that one is standard normal. So this will be depicted here for bivariate Gaussian as a circle if you have isotropic Gaussian. Either we set initial values. So this means that I need to describe the tangent vector at the standard distribution, and the tangent vector of mu sigma is a vector v and a symmetric matrix because the tangent vector on the SPD cone is a vector of symmetric matrices. So I just show here the initial condition in blue for mu, and I take the two eigenvectors of the symmetric matrix to show the initial condition for the matrix part. Okay, and or you want to solve this second order. So this is going to be solved in the 80s. I will show you. And this was open problem. Is if you fix targets like initial and final, you have to solve for all t between 0 and 1. And this was a very difficult problem. And to further compute the Rao distance, we need to integrate the length element along the geodesic. Okay. So two difficulties that was open so far was to have closed form for boundary values and to make integration along the closed form geodesics. What Ericsson did in 1987 is that he solved the initial value condition. So this is, I will call you the equation. And for solving that, he introduced what we call now natural parameterization, because the multivariate Gaussian is an exponential family. And he used the natural parameters somehow, but he didn't really mention it. And he get out a solution like that. So I'm not going to enter into details, but basically what you do is somehow you increase the dimension by 2d plus 1. Okay? You embed your mu and v into this matrix. You compute the matrix exponential, and from that you retrieve some part of the 2d plus 1 matrix to get the natural parameterization along the geodesic, and then you convert back to the original parameterization. And the proof was done algebraically, but no real geometric insight. Okay, it was said, okay, it looks like homogeneous space somehow, but no very clear explanation. And this has been a mystery for almost 30 years, right? Even more. So the direct solution for without increasing the dimension was done by Calvo and Euler in 1991, but also with initial condition, not with boundary condition. Here you can see that you have matrix, sinus hyperbolic, and matrix things. So I leave the things here. You can program because everything is written to that. And then you have the matrix pseudo-inverse here somehow. But this was also known in 91. In the case where mu is constant, is also known because it defines a totally geodesic submanifold, and it was solved in 1973. And this is a well-known formula that we meet many times when we study covariance matrices or positive definite matrices. We get this metric distance here, which is a Rao distance for center multivariate normals. And in that case, what we have is not only do we have invariance by positive affine group, but we have also invariance by inversion. You can check it here somehow. If you take the inverse, it will not change the things here because you have a log square. Okay. So, in the case where you don't have mu is constant, you can write all the things: initial condition, boundary condition, Rao distance in closed form. You have everything that is very clear for implementation, and it has been extensively used, and it's really well known. In the case that you want to have the matrix, the submanifold with the covariance matrix fixed, here you can bound by the Malanobis distance, but it is not totally geodesics. For example, here this blue, if you integrate the length element along this blue line, it will be much longer than this red this red geodesic here, which is a real Fisher-Rao geodesic. And but what you can show, some work that has been done, is you can express in closed form this solution according to the Malanobis divergence. Okay, and this is not so old result somehow. So the breakthrough was a paper by Kobayashi in 2023. He revisited Ericsson paper, but he made clear why we take 2D plus 1 dimension and what it means to extract part of the matrix to get solution to the geodesic. So I'll let you read the paper if you're interested. Here, this is just the recipe. Okay, the recipe is that you have two normal distribution and you want to make the geodesic with boundary condition. You're going to create again 2D plus 1 matrices like that. Okay, so you will have M1, M2, and D1, D2. And what you are going to do is to consider this matrix G, like for Gaussian in higher dimension, if you like, as a kind of Bloch-Cholesky. It's what he calls Bloch-Cholesky decomposition here. And then you will simply use the geodesic of SPD matrices in dimension 2D plus 1, and you will extract. And this extraction, he interprets it geometrically as a Riemannian submersion. Okay, so geometrically speaking, this is very well understood what's going on somehow with from Ericsson in the 80s to this year. Everything was already algebraically in Ericsson paper, but it was extended very simply by having these geometric insights. So I'm going to use it to design. So this is a kind of geodesics that you get. Okay, I fix initial and final condition, and then I just apply this recipe that I show in the former part. So now, a geodesic, we know that it is a totally geodesic submanifold, right? So what I'm going to do is I'm going to cut the geodesic in T parts, and I'm going to bound the Fisher-Rao in each part. Okay, and if I do that, I will upper bound also the Rao distance. And to upper bound the Rao distance on one part, you can show that the square root of the Jeffreys divergence, which is the symmetrization of the Kullback-Leibler divergence, is upper bound. Okay, so this is also this is coming because if you take for very close by, also in the limit case, if you take for very close by Gaussian distribution, you have the F divergence like the KL or Jeffreys divergence that writes like as a length element, and here you have the rescaling by that. And for Jeffreys, F prime prime 1 is 2, so you get just equality here, or more generally here. So this is also something that you could get, that the Rao distance in general, even in general, not infinitesimally, but in general, is upper bounded by the square root of Jeffreys divergence. So let me see if how much time do I have?
7 minutes.
Okay. Okay. Somehow it's not. Okay, it's not the right slide version that I have here. So in the archive report, from this perspective, given epsilon precision factor, I design a 1 plus epsilon approximation. So the algorithm is very simple. It's based on this fact, and I invite you to look at the archive. Okay, but the thing is that we need to compute inverse of matrices and also traces. So what I want now is to take a second approach to define another metric distance for Gaussians. And we are using this diffeomorphism that was written in Calvo and Euler in 1990. I am going to embed the Gaussian mu and sigma into D plus 1, not 2D plus 1 this time, but D plus 1. Okay, I had my matrix with just one column and one row. And if you use the trace metric for this cone in dimension D plus 1, and you apply this formula, you will find this, okay, for this parameterization. And if beta equal 1 and is constant, this term vanishes, and then you get the Fisher-Rao metric for multivariate Gaussian. So you will have an embedding into a submanifold of codimension 1 into the cone of dimension D plus 1, but it is not totally geodesic. Okay, so this is what's written here. So what we are going to do is simply to apply the formulae for the positive definite matrices in dimension t+1, and because it is not totally geodesic, I know that this is going to lower bound, this time a lower bound, okay? And this is what Calvo and Euler did in 1990, and we end up with this lower bound here, okay? And by cutting it on my closed form solution for Rao geodesic, I can get very fine approximation, okay? Now, one thing is that you want to avoid in the former, let's say here, what's a bit annoying is that you need to compute the eigenvalues, which is time consuming because you need to decompose. What you can do to have the midpoint geodesic is to use an extension of the arithmetic harmonic mean. So what you are going to do is you start from sigma, so you take sigma 0 and sigma 1 to be your input. You're going to compute the arithmetic mean, and then you're going to compute the harmonic mean, and reiterate like that. And if you do that, you can show that with quadratic convergence, you will get what is called the matrix geometric means here, which is the geodesic midpoint. It's a Riemannian center. Okay. So what I propose to further speed up is to use this Calvo and Euler embedding, but in the cone here in a higher dimension, to use a fast distance. And I'm going to use the Hilbert metric. So the Hilbert metric just uses the maximum and minimum eigenvalues. So I will have the closed form. And because I use it on a submanifold of Gauss dimension 1, in general, this is just a projective matrix in the sense that if you multiply by two scalar lambda and lambda prime for P0 and P1, you will get the same value here. So you don't have the law of indeterminables. But if you restrain it to the embedded submanifold of codimension 1, it becomes a metric. And here we bypass the eigenvalue decomposition. So it's going to be very fast. And also the geodesics on the cone are just straight line, and then you pull back to get the path into the multivariate Gaussian. So this is a bit what's going to be explained here. And just as an application, for example, so here we have two bivariate Gaussian, input, output. In black, I show the Fisher-Rao geodesics that are discretized, with the recit that I show. And in orange, I show the Hilbert pullback, okay, which is very fast. And based on that, I can compute, for example, if I'm given a set of Gaussian mixtures, and if I want to quantize them or if I want to cluster them, I can cluster according to the enclosing ball. I will show you the enclosing ball according to the Hilbert pullback metric here, which will be shown here in green. Okay, and then you can use it as an algorithmic framework. So this is the summary. So in this talk, I show two things. One, to get 1 plus epsilon stable, numerically stable, and even for very far away normals, which was not the case so far. People have been looking at very complex solutions before of Rao distance between multivariate normals. This is the algorithm that is written here. So this is this kind of algorithm. Actually, it's a bit it's a recursive algorithm, because I cut the geodesic in half. If it's still lower bound and upper bound, is still the ratio is still above 1 plus epsilon. I further cut and cut and cut. Okay, and you will get here the Fisher-Rao distance written here, and you will get also the epsilon that I choose to show you how it has been cut. This is a cutting point in between. Okay, so as you increase the precision, you need to cut more the geodesic to get the thing. Okay, so this concludes this talk. We presented the result of Kobayashi for geodesic with boundary value condition in closed form, and we use it to design a fast 1 plus epsilon approximation. And I further propose another metric based on Hilbert distance. Okay, thank you.
Thank you.
Are there any questions or comments? So do you have an idea of the complexity of the algorithm when you're absolutely small? Like how many pieces do you have to cut, for example? Does it increase a lot or not? Exponential or?
Actually, I have a better algorithm now, but not yet written. So I will make analysis on this better algorithm. So
okay. So would you say quadratic, exponential?
I have no idea. You can have a look here, for example, because here I think I increase. If you look, here precision is like 10%, 1%.
Oops.
So here I increase the precision by tenfold each time, from here to here, and you see the discretization along the path.
Almost linear
Yeah.
seems okay.
But we have better now, I think.